So let's get started with CH5010. So we are in the last week of this course. Uh, Last day, we'll go over what we have done in the entire 13 weeks. We'll start kind of at the end and then move backwards, so that the most recent ones will recap it. We have already beginning of uh, these last three modules. We have already recapped the stuff from week one, right? So we'll do that. Uh, Recapping for rest of the modules. Okay. So we were talking about fixed bed reactors, reactor level modeling for fixed bed reactors. So various levels of modeling. Before going to that, we talked about what we are looking at when it comes to fixed bed reactors. Said that the fixed bed, although we are talking about fixed bed over here, but all of these are applicable to various different situations. Fixed bed reactors, wall coated uh, reactors where the catalyst is coated on walls, which is what you see in monolith reactors. Gas liquid reactors, liquid reactors, all of them, all of these concepts are really valid. Okay, so you have things that are happening at the reactor level, that is shown in the black box, and you have things happening within the catalyst or within a particle or within a liquid drop or a gas bubble. Okay, so there are things that are happening. So because of processes taking place in the particle or inside a bubble, uh, you need time, and I can pause for a few minutes. Okay. So there are processes that are happening, within the bubble that affects, or within the catalyst particle or within the reacting particle that affects overall how the reaction is taking place or how the conversion is taking place in that entire reactor. We talked about the example of a conveyor belt and us taking food from the conveyor belt. Okay. Uh, of course, the size of this room in our imagination is much larger than probably the conveyor belt, but think of it in a very opposite way. Think of us being a very small particle inside a large reactor. Okay, so outside world is much larger than this room, and that's why we are only able to pick up a few plates from the conveyor belt and not the entire food. So what did we do in the previous class? In the previous class, we looked at two things. Like module 8, we looked at solving a PFR. Like module 5b, we looked at looking at one one particular catalyst pellet. Okay, problem 3 was essentially about combining all of them. Uh, the type of models that are there, various different types, pseudo homogeneous and heterogeneous models. So pseudo homogeneous models are the models that you have seen already so far. So species balance and pseudo homogeneous. Species balance is d by dv equal to rk. Okay, you can multiply or, or divide by this is dw. Okay, so this leads us basically this and this are equivalent to each other. Okay, something that we have done right in the first module. We had very briefly talked about this. Okay, essentially that's the same. Energy where Q is the heat transferred multiplied by area of heat transferred divided by volume. Okay, so this is how you can write this. This we can always write this as dq. Okay, this is how we might even be able to write this. And if we divide this by rho b, okay, we'll be able to write this as okay. These are all equivalent. Okay, you can make any of these conversions. It's all there. I mean, you don't need to write it down. It's all there in the slides later on. So you can write it like this. You can write the energy balance like the one given at the top and just multiply divide by rho b, and you will get rho b multiplied by summation of delta H j r double dash. So that's also fine. They are all basically equivalent to each other. Okay. Which equation I should use and all that, don't let that really confuse you. Use the equations that are really convenient for you to use given the data in the problem. Okay, so let's go to any questions so far, confusions. Yeah, we'll come to that. Yeah, thanks, good question. Okay, so this is assignment 5. Is this week good enough for assignment 5 submission, or you want more time? One extra week? You want time right up till 20th so that you have your answer sheets with you? Our exam is on 20th. You know that, right? So the exam will be on 20th, 40% of the grade. Yeah. And we have one decision to make. So I have to send a Google form today. Whether or not we will kick out one of the modules. Problem number 5 is essentially very similar data as your tutorial. Okay, actually lot of the numbers are not even different from the tutorial. Okay, the reason why I've done it like that, for two reasons. One is so that you can connect. The way I've done the tutorial is you can connect example 1 with what you have done or what you can do in PFR. You can connect example 2 with the Thiele modulus and eta. Okay, combine example 1 and example 2 and just replace KCA with eta multiplied by KCA. That becomes example 3. Okay, that's how we have tried to connect on Wednesday, 30th of October, the tutorial, that the previous class that we had, the tutorial that we had, that is how we had tried to connect. what data was given to you? The data was given to you in a form that you can pretty much directly apply the equations. You don't have to think about the equations, you can directly apply the equations. That's not how the data is usually available in the literature. Okay. In the literature, the data is often given in catalysis, data is often given in terms of per kg of catalyst or per gram of catalyst. Okay. It's always normalized with respect to per gram of catalyst or per kg of catalyst. Now, why do we do that? For example, if you want to run isothermal reactor, what we will sometimes do is we'll take 100 milligrams of catalyst, we'll mix it with 900 milligrams of diluent. Some of you might have gone to the lab and you would have seen the reactor over there. If we expect the reactions to be highly exothermic or highly endothermic, we will dilute the bed, and the same reaction will be carried out in a larger amount of bed. Alternatively, if the exothermicity is not very high, we will use the bed as is without dilution. That is when we are doing the kinetic experiments. Once we get the kinetics, then when it is put in a reactor that we need to design, at that time we are not usually not going to dilute the reactor unless we expect thermal runaway. Okay, have you heard the term thermal runaway? Yes, no? Thermal runaway basically means that the rise in temperature is faster than our ability to take the heat away, and it can cause significant rise in temperature, and then the internal catalyst material or internal structures can, for example, melt, and it can cause a dangerous situation. So you don't never want to go to a thermal runaway type of situation. Okay, so when you go from a diluted bed to a concentrated bed and so on, what really remains constant is not the rate of reaction per unit volume of the bed, but rate of reaction per unit mass of the original catalyst. Okay, that's the reason why when it comes to literature or when it comes to industry, most of the time you will get the data in terms of per kilogram of catalyst, okay, which is R double dash. Okay, so in module 1, how did we treat R double dash? We treated R double dash in this particular manner. Okay. Now, when it comes to your catalyst bed, there are two densities. Okay. There is density of catalyst . Okay. Why are there two densities? Is because this is how the bed would be. Okay. The density of this guy is rho p. Void fraction of the bed is epsilon b. How do you think the density of the bed is related to density of the pellet? What is the fraction of gases in the bed? Epsilon b, right? Therefore, what's the fraction of solids? 1 minus epsilon b. Therefore, what's the density of the overall bed? Rho p multiplied by 1 minus epsilon b. Okay, 60% void, 40% solids. How much solids are there? Original density of solid is let's say 1 kilogram per liter. Okay, in 1 liter of the bed, 400 ml or 40% is solids, so it is 40 grams that is present. So, 40 multiplied by 1, where does 40 come from or 0.4 comes from? 1 minus epsilon b. Where does 1 come from? Rho p. Okay. So, that is what the density of the overall bed is going to be. Okay. So, when it comes to your this is the density. That would come in. Okay. When it comes to what happens in a pellet, this is what comes in. Why? Because pellet is that particular solid itself. Okay. Where is 1 minus epsilon b coming in? 1 minus epsilon b comes in because all of this gap, there is no solid over here. Wherever I am drawing those red dots, there is no solid. These are all fluids. Okay. That is the reason why this comes in. Okay. If you are going to do df by dw, do you need to change anything? No, you do not need to change anything. Why? Your rho b, you take it to the left hand side, you will get dfk by dw equal to rk double dash. Okay. So, let us say you have calculated the weight, the total weight of the catalyst bed that is required is 20 kilograms. How much volume will that 20 kilograms occupy? It will not be weight divided by density of pellet, it will be weight divided by density of pellet is the amount, is the volume of only the pellets without counting the gas. The volume of pellet plus gas is going to be 60% higher. That is how you get this. So, your dw, from dw you calculate the total w divided by density multiplied by 1 minus epsilon b will give you the total volume. Okay. Either ways you can use either of those equations. That is what you need to do in your assignment, no other difference. Okay. Internal diffusion in the pellet, we will do the same stuff that you did in module 5b, but using the data the way it is given in the industry. Okay. So, the numbers are actually almost the same. DAM is 0.024, this is the diffusivity of small alkanes at around 550 kelvins. Okay. K double dash and rho p are given, and from K double dash and rho p you have to compute the rate constant, use the rate constant in Thiele modulus. Okay. Recall we did two types of Thiele modulus, your generalized Thiele modulus and your regular Thiele modulus. What is the generalized Thiele modulus? It is based on slight change so that all of the lines eta versus phi fall on approximately on the same line. So, it makes your computations just easier. Okay. What is the regular Thiele modulus? Based on the fact that it is a spherical pellet. Okay. So, that is what this is going to be. Okay. Pseudo homogeneous model, as I just said, you can use df by dv or df by dw, either one. If you use df by dv, you will calculate the volume, from volume you calculate the density, the mass of the catalyst. If you use df by dw, you will calculate the mass of the catalyst, from mass of the catalyst you calculate the volume. Okay. That is what you need to do. For this assignment, any 5 out of the 6 problems. Okay. So, there are 6 problems also given to you. You can solve any 5 of the 6 problems. The 6 problems comes from our research. Okay. The kinetics that I have given to you is kinetics from probably, I mean, from 35 years back, graph kinetics. So, we do not use the exact same parameters anymore, but the form of the kinetic expression is similar. Okay. So, the first question relates to your understanding of thermodynamics. Okay. The second question relates to your understanding of external diffusion, module 5A. Third question is mostly your understanding of model equations, module 1 and 2 as well as module number 8. Okay. But we are going to do what is known as 1D heterogeneous model. What that 1D heterogeneous model is what we are going to talk about in the next 10 minutes. Okay. This was the last slide that we did in the previous lecture, Tuesday's lecture. Okay. So, these are the model equations. Okay. And as you asked, is also when it comes to liquids, pressure drop is just calculated in order to ensure that you can run this fixed bed reactor without a problem. For example, if the fixed bed reactor is very large, the pressure drop is going to be very significant, and it will be difficult to or you may not want to run the reactor with a pressure drop of 10 bar and so on. Okay, that is what for liquid cases you get. For liquid, volume is constant and therefore velocity is constant. Okay, not for gases. For gases, you will use the pressure drop equation. What will you usually use for pressure drop? Ergin's equation. Okay. No, so we have our species balance. We have our energy balance. Okay. In addition, you have your pressure drop equation. Okay. Now, what else is needed? Your reaction terms. They have concentration. Okay. In liquids, volume is approximately constant, which implies in gases. We loop back to the very second problem of your first assignment or first problem. Pressure and conversion are interrelated if it's a gas phase. Okay, the same idea for gases. okay, or okay, C total P total by RT. F total is Q multiplied by C total. Okay, and this is the way you can actually get the overall concentration from your flow rates. How? This will give you basically F total is something that you can calculate, P total you get from dP by dz, temperature you get from your energy balance equation, and therefore you can get Q. Okay, if you get Q, you will be able to then calculate your C. Okay, and you will just have your Z coming into your Q equation. Okay, and remember your epsilon and deltas and all those things, those are all coming in from this expression. Okay, and how those are related? Problem 2 of assignment 1, if you want to go in that direction. Okay, so that's what connects your various things. Okay, this slide is there for you. Whether you want to go with this slide or whether you want to go with what is there in Davis and Davis, whether we want to go with what is there in Froment and Bischoff, or you are more comfortable with your undergraduate book. Choice is up to you, completely up to you. All the 4 books, the final expressions, interestingly, the final expressions in all of the 4, this Froment and Bischoff, Davis and Davis, and Fogler. I have not seen Leavensfield, but Leavensfield and Fogler are usually similar. The final expressions are different in all 4. Okay, but they are all just algebraic manipulations of each other. They are absolutely the same. Okay, there is really no difference about them. Okay, I am just telling you how to calculate. I am just giving you an expression that can be used irrespective of number of reactions or number of species. Okay, Levenspiel's expression, final expression, the boxed expressions, right? Those are the ones that lot of times for gate and all that we tend to look at. Those boxed expressions are the ones that are derived finally for individual cases. You can correct it. ZRT it will be, yes. Yeah. Okay. So yeah, another of GANs. Okay. We have solved a similar problem earlier in using Fortran, using Excel. That was A going to B reversibly. This is A going to 2C. Okay. Here R2 is this. Okay. RA is minus 1 multiplied by R2. RC is 2 multiplied by R2. Okay. This is a problem, this is a confusion sometimes amongst both chemists and amongst chemical engineers. Chemists usually do experiments where they are measuring how C is changing. So, they are actually calculating capital RC. Okay. Chemical engineers would be looking at A is the limiting reactant and therefore will be calculating small Ra, which is nothing but nu multiplied by negative nu multiplied by capital Ra, right? We have done that before, right? So, that is what this is. So, split the stoichiometry from the rate. The rate is given to you. Multiply that stoichiometric coefficient to get the capital R. That is the reason why I have distinguished between using small r and capital R. In my research, I do not use capital R's, I use small r's only. Only for this class, I have used capital R's so that that confusion is not there. Okay. So, this was student request a couple of years back. We will take up an example where we are going to consider pressure drop also, that we will do in next to next class. Okay. This is what you are going to do in your assignment, just what I told you about. Okay. In the pseudo homogeneous model accounting for internal diffusion resistance, you calculate your eta. If it is a first order reaction, your eta is independent of concentration. If it is non first order reaction, your eta depends on concentration. If eta depends on concentration, your equation this eta is no longer a constant number, it just varies with concentration. Okay, that is all. Okay. And this is the Ergun's pressure drop equation. We will skip the axial dispersion model. Okay. And Ergun's equation and all that, do not waste your time remembering those things. Okay, either it will be, if it is a closed book, closed notes exam, I will provide the formula sheet. Okay, please do not waste your time remembering complex formula where forgetting one thing here and there, but straightforward formulas, please, yeah, that. Okay, so you have to get in my mind and determine what straightforward is, but essentially, I do not intend to give any trick questions. You would have noticed in your quiz, these are not meant to be trick questions, these are meant to be questions that will test a particular concept. It might feel like a trick question because I am testing concept X and you think it is concept Z. that will feel like trick, but they are not intended to. Each and every question, not a problem. Problem is intended to test a few concepts, 2 or 3 concepts. Each question, right? Number 1, 2, 3 that I have, that is intended, usually intended to test only one concept at a time. Okay. So you, that's how you would want to kind of prepare for the exam. Okay. Tomorrow we will take up a 1D heterogeneous model example. Okay. Just the way with internal diffusion, we combined two things. We combined the concept of eta and we combined the concept of PFR. Same way in 1D heterogeneous model, it's external diffusion and reactor. Okay. So, how does 1D heterogeneous model work? This is catalyst. Okay. External diffusion, K multiplied by CAS. So, if you look at this particular control volume, okay, the mass that is disappearing because of reaction is, or sorry, a concentrate, the moles that are disappearing because of this reaction is given by this. So, you will have okay, Kg Ca minus Cas is in terms of per meter square catalyst surface area. So, multiplied by a catalyst surface divided by volume, okay, or we will represent this as A by V. Where did we encounter this first? Module 5A. Okay, and what happens on the catalyst surface? Same thing that we did in module 5A. Okay, what did we do in module 5A? The first equation was equal to RA. The second equation, we did it exactly the way it is, right? Okay, in module 5A, this module, okay, we will do this tomorrow, where this is just a quick preview into what we are going to do tomorrow, okay, alright.